Hello everyone, my name is Xiaobing Sun. I'm very honored to introduce our paper, CubeFlow Money Laundering Detection with Coupled Tensors. This work is advised by Shenghua Liu and joint work with Jiabao Zhang, Qiming Zhao, Jinglei Chen, Ruoyu Zhuang, Huawei Shen, and Xueqi Cheng from Institute of Computing Technology, Chinese Academy of Science, and China Construction Bank Fintech. Jiabao Zhang and Qiming Zhao contribute equally with me as the first authors. Money laundering is the behavior to conceal the source of money achieved by illegitimate activities and always be a fast process involving frequent and chain transactions. Generally, the process of money laundering typically involves three steps: placement, layering, and integration. Placement puts the dirty money into the legitimate financial system. Layering conceals the source of the money through a series of transactions. In the final step, integration, illegal money is withdrawn from the legitimate account to be used for whatever purpose the criminal have in mind for it. And we focus on the second steps. In money laundering activities, a high volume of funds needs to be transferred from source to destination accounts with limited number of middle accounts. Therefore, it will create dense blocks in the transaction network, and will use candidate to denote a collection of accounts that may be involved in money laundering. Here we summarize three typical characteristics of money laundering: density, zero out middle accounts, and fast in, fast out. Density means intensive transfer will form dense blocks in the network. Zero out middle accounts refers to the middle account can be regarded as a bridge in money laundering. Most of received money will be transferred out. Fast in and fast out means the above process is usually done within a very short interval. We can see that suspicious dense blocks forms a transfer flow through a middle account, which is not found in the natural dense blocks. So how can we utilize the above characteristics to distinguish suspicious dense blocks? Our solution is modeling transfer flow as two coupled tensors. As this figure shows, for one middle account, the transactions which transferred into and out of it will create two fibers in the coupled tensors. We use blue for a low volume of funds and red for a high volume. If we extract the suspicious transfer flow which starts from source and with destination and is done in the same time bin, we can obtain two coupled dense subtensors which have similar mass. Moreover, for all suspicious middle accounts, it will be gathered into two more denser blocks like cubes. So we want to spot such dense blocks from original coupled tensors. CubeFlow detects earliest and accurately in real-world transfer data. We also use the Pareto distribution in the extreme value theorem to fit the mass of transfer flow, and the densest blocks found by CubeFlow shows very suspicious. To verify the effectiveness of algorithm, we conduct injection experiments under different settings. As shown in this figure, CubeFlow outperforms other baselines. Finally, our method scales nearly with the number of the non-zero entries. Our formal problem definition is, given two coupled transfer tensors P and Q, how can we detect two dense blocks? The most classical approaches for money laundering detection are those rule-based models, such as using decision tree, Bayesian network. However, these methods are highly dependent on expert knowledge. Besides, machine learning models such as SVM and natural network are also applied. However, these methods use supervised learning and need a large amount of label data, where the availability is low. As for the flow-based models, flow-scopes are designed for dense money laundering flow. However, it fails to consider other important attributes such as time, because the limits by the graph. Many dense block methods also can be used for money laundering detection. However, these methods are proposed for general-purpose anomaly detection tasks, which not focus on the flow across multi-step transfers. Now we will introduce our model. We model the transfer flow as two coupled tensors. The purpose of detection is to find two dense blocks in original coupled tensors. In general form, we can define the minimum and maximum value between total money transferred into and out of a middle account, with other attributes are also fixed, as F and Q. Here, M represents the mass of two fibers created by transfer flow. Then we can define the remaining money as the difference between the maximum and the minimum value. Next, our money laundering metric can be defined as this formula. The more suspicious dense block will make our metric become larger. Specifically, for the numerator, the higher the amount of flow will make F larger. And if the flow satisfies zero out middle accounts and fast in, fast out, R will be small. Additionally, the denominator represents the sum of the size of different attributes of subtensors. To develop an efficient algorithm for our metric, we enfold the tensor P on X mode and Q on Z mode. Then we use I to denote the number of columns of the metric to approximate the denominator. Now let's introduce our algorithm. First, we build priority tree. After unfolding original coupled tensors to matrix, we initialize the subtensor BP and BQ with P and Q respectively, and S represent the union of three sites I, Bx, and Bz. Then we calculate the priority weight for every index in set I in step 4. For the index belonging to the set I, we assign weights for them according to our metric. As for the index belonging to Bx and Bz, their weights equals to the total amount of money transferred out of and into them. Therefore, we can build a priority tree for index in the set I. Second, we perform the greedy deletion as follows. In step 1, we will find the minimum weighted node in priority tree, that is -0.8, and we delete it. In step 2, we will update node-wise for all neighbors of delete node, that is x1, and update the value of our metric. The above process will be repeated until one of the sites I, Bx, and Bz is empty. In the second iteration, we once again find the smallest value, -0.6 first, and update all its neighbor nodes. Meanwhile, we can find G is still rising up. In the next iteration, we continue to delete the smallest node and update the weight. In the seventh iteration, when we delete the third node with a weight of 4, all nodes inside I are deleted, so we will stop the iteration. Finally, two dense blocks that we have seen with the largest value of our metric are returned. Now let's show our results. We use two real-world transferring datasets to verify the effectiveness of our algorithm. CBank data from a anonymous bank under an NDA agreement. CFD data from Czech bank released for discovery challenge. Here we model CFD as 3-mode and 4-mode tensors, called CFD3 and CFD4 respectively. We vary the density of injection on CFD3 dataset by ascending amount of money and descending the number of accounts. We can see F measure of our method always close to 1, achieving the best results. To verify the robustness of our method, we evaluate the performance of CubeFlow against different injection ratios. CubeFlow outperforms other baselines and have obvious advantages. We scale the amount of dirty money laundered by the real labeled fraudsters in CBank data. Our method can detect money laundering behaviors earlier and stably, with a high accuracy. We sampled 5,000 uniformly random flows from CBank data with the same size as the densest blocks detected by CubeFlow. As this figure shows, mass of sampled flow follow a generalized Pareto distribution, and the top one flow we detected shows very suspicious. We also conduct injection experiments on CFD 4-mode dataset, and CubeFlow still performs best. Finally, our method scales nearly with the number of non-zero entries. In this paper, we propose a flow-based money laundering detection method, CubeFlow. The suspicious metric we design can utilize the characteristic of money laundering flow. Our method is effective and robust to spot the fraud in big attributed transaction tensors. Our code is available at the following link. Thank you.